Morning everyone, thanks for joining us for the first live group tutorial of the day. This morning's chemistry session is on gas volumes and a summary of the topic, so should be really helpful this morning. This will be a 1 hour session as normal, so we'll end at around 11:15. I'm Tilly, I work at my tutor, and our tutor today is Aman, who lots of you know already. Aman's been teaching all of our chemistry sessions so far, and lots of you know her really well. If you have any questions for either of us throughout, just drop them in the chat or the Q&A. Aman will keep an eye on the chat throughout, but we'll also have some time at the end of the session to go through any questions we may have missed, so don't worry if your question isn't answered immediately. We'll make sure to have some time for those at the end. All of these sessions that we run are recorded and put on the My Tutor YouTube channel. So if you wanted to catch up on any past chemistry sessions, you can do so there, or any of our other subjects. So as lots of you know, we also have biology, we have physics, English, maths, both higher and foundation, and history. So if you wanted to catch up on any of those, just head over to the My Tutor YouTube channel. I'll just wait a couple of moments as people join us. As I mentioned at the start, any questions, just let us know in the chat or Q&A, and we'll keep an eye there. And this session will be running through content and then some time for questions at the end. Brilliant, you all ready to go, Aman?
Yep, that's fine.
Great.
And welcome back everyone. So as Tilly said, today we're going to be looking at gas volumes, and then it will be a overall summary of everything that we've done with regards to quantitative chemistry. So starting off then, today we'll be looking at what the molar gas volume is and how to use it, which I should say these are higher tier topics. So gas volume is a higher tier topic, but the summary that we'll be doing will be a cover of all of the foundation and higher tier questions. Then able to apply that equation. So the equation is moles of gas equals the volume of gas divided by the molar gas volume, which we'll go over in a bit. And then be able to apply all of the equations we've learned to a range of questions. So that's just about the summary there. So hopefully we'll be doing quite a few exam questions today as a summary of all the quantitative things that we've learned. Before we get into molar gas volume then, I know on Monday we were cut off a little bit with time, so we'll do a quick recap of what we covered with regards to titration reactions and concentration calculations. So the first question here, it says, write a balanced equation for magnesium hydroxide reacting with hydrochloric acid. So magnesium hydroxide. First of all, hopefully if you remember from Monday, we need to start off by knowing what the ionic charges are. So does anyone know the ionic charge on magnesium? If not, we can look at the periodic table. So what's the ionic charge on magnesium? Okay, so I'll tell you it's in group 2. Does that help? If it's in group 2, what does that mean? What charge does it form when it forms an ion? Yep, 2+ ion. So if Mg or magnesium is a 2+ ion, that's great. What about hydroxide? So we went over this on Monday. Does anyone remember what the hydroxide ion charge is? OH-. Excellent, well done. So magnesium hydroxide then, when they combine, we've got magnesium has 2 electrons that it wants to donate, but hydroxide can only accept 1. So what that means is that we need 2 hydroxides to accept 2 of magnesium's electrons. So it will be MgOH2. Remember, that's MgOH2. So that's magnesium hydroxide. Does anyone remember the formula for hydrochloric acid? Does anyone remember that? HCl, excellent. So MgOH2 plus, oh, okay, just give me 1 second. Hi Tilly, can you still hear me?
Yeah, I can still hear you fine.
The lesson space has just stopped working, so just give me a second.
Okay, let me know if you need any help. I'll just answer a question we've had through in the meantime, which was, is biology higher happening this week or next week? So just sometimes we have specifically higher biology sessions, and it will say on the timetable in brackets that a lesson is higher. Otherwise, usually our biology sessions sort of cover a range of levels, so it will be sort of just your regular level that will be useful for anyone, and then also a bit of higher.
Okay, so you should be able to see my screen again now. So we're working on magnesium hydroxide, which we said was MgOH2. And then we've got hydrochloric acid, which everyone said was HCl, which is excellent. And then what does that form? So does anyone remember when we do titration reactions, so when we react an acid and an alkali together, what do we form? What are the two products? Okay, so someone's asked a really good question. How do you know when to use brackets or to do a big number in front? So when I've done magnesium hydroxide there, we know that that is one magnesium reacting with two hydroxide ions, so it's MgOH2. If I put a big 2 in front, that means that the ratio still stays the same, so it's still one magnesium to two hydroxides, but when I put a big 2 in front, it now changes the ratio to two magnesiums to four hydroxides. So the numbers in the actual compound relate to the ratios, but any big numbers in front of the compound just multiply that ratio. So you can see the ratio has not changed, it's still 1 to 2, it's just a multiple of it. Whereas when I did MgOH2, that was making that ratio 1 to 2. Yep, so what do we think is formed then when we react magnesium hydroxide with hydrochloric acid? So it's a titration reaction. Excellent, someone's saying magnesium chloride plus water. Excellent, so yeah, we form a salt and water. So magnesium chloride, so Mg, we remember, is a 2+ ion, and chloride, does anyone know what ion charge that has on it? I'll tell you, it's in group 7. Oh, yeah, 1-. So if chloride has a 1- charge and Mg has a 2+ charge, it's just like magnesium hydroxide, where we need two chlorines to react with magnesium. And that's because magnesium has 2 electrons that it wants to donate, but chlorine can only accept 1. So for magnesium to remove both of its electrons, it needs to react with 2 chlorines. So it produces MgCl2. And then the water, as we know, is just H2O. If you're wondering about state symbols, remember everything is aqueous apart from the water. So aqueous, aqueous. So our acids and alkalis, remember the definition of alkali is that it's a base that is dissolved in water. That's how I know that the magnesium hydroxide is aqueous. Hydrochloric acid is hydrogen chloride dissolved in water. Therefore, it's aqueous. The salt formed will also be aqueous, and water is a liquid. So that's the state symbols. Now we just need to balance it. So remember, we always look at what is different between the reactants and the products. So if we look at the reactant side, first of all, we can see that there's 1 chlorine on the reactant side, but there's 2 on the product side. So if I put a big 2 in front, again, that's not changing the ratio. The ratio is still 1 hydrogen to 1 chlorine. We've now multiplied it, so it's 2 hydrogens to 2 chlorines. So the ratio is still staying the same. So we've now got 2 hydrogen chlorides. If we have a look at our hydrogens, there's 2 hydrogens in magnesium hydroxide and 2 in hydrochloric acid. So there's 4 in total on the reactant side, but on the product side, there's only 2. So we need to put a big 2 in front of our water. And now everything should be balanced. We've got 1 magnesium, 2 chlorines, 2 chlorines, 4 hydrogens, 4 hydrogens, and 2 oxygens, 2 oxygens. So that's a fully balanced equation for magnesium hydroxide reacting with hydrochloric acid. Does anyone want me to go over that again, or are we happy with that? Just a reminder that if you are struggling with writing these equations, we went over this in quite a lot of detail on Monday. We definitely wrote a lot of balanced equations then. Okay, so the next question then is 10 centimeters cubed of sulfuric acid were required to neutralize 25 centimeters cubed of calcium hydroxide with a concentration of 0.2 moles per decimeter cubed. Calculate the concentration of the acid. So does anyone remember the steps for this, or what steps I went through on Monday, how we calculate the concentration of something? What's our first step? Excellent, someone's saying work out the moles first. Well done. So what we always do is we look at which one has the most information. So that means which, either the acid or the alkali, which one has the most information. So if we have a look in our question, we only have the volume of our sulfuric acid, but we don't have any other information about it. So that means we can ignore the acid for a second. So now we just need to look at the alkali, and we can see we've got 25 centimeters cubed, which is the volume, and a concentration. So as someone said, we can calculate the number of moles of calcium hydroxide. So the equation for concentration is concentration equals moles over volume. So that means that when we rearrange that, if you think about it in the triangle form, If here's concentration, here's moles, and here's our volume in decimeters cubed, that means the number of moles equals the concentration times the volume. So our concentration is 0.2 and our volume is 25 centimeters cubed. So remember, to convert to decimeters cubed, we divide by 1,000. So that would be 0.025. We then multiply by the number of moles, which is 0.2. And if you do that on the calculator, you will get the number of moles of calcium hydroxide. So that will give you an answer of 0.0005, so 0.005, and that's the number of moles of calcium hydroxide. So now that we've got the number of moles of calcium hydroxide, what do we need to do next? So we've worked out the moles, what's the next step? Okay, so remember then, the next step is to look at a balanced equation so that we can identify the ratio of calcium hydroxide to sulfuric acid so that we can work out how many moles of sulfuric acid there are. So to do that, we need to write a balanced equation. So a balanced equation, remember, for calcium hydroxide, does anyone know the charge on calcium? I'll tell you it's in group 2. What charge will a calcium ion form? 2+, excellent. We've already said the hydroxide ion is OH-, so just like magnesium hydroxide, it will be CaOH2. And that's because hydroxide has a 1- charge, calcium has a 2+ charge, so it has 2 electrons it wants to donate, but hydroxide can only accept 1. So for hydroxide to accept both of calcium's electrons, there must be 2 of them. We're adding that to sulfuric acid. Does anyone remember the formula for sulfuric acid? So we went through this on Monday. We went through all the key acids and alkalis. Yep, excellent, H2SO4. So H2SO4. Excellent. Okay, what's our salt that we're going to form then? So we've got calcium hydroxide plus sulfuric acid. So we know we're going to form a salt and water, as with magnesium chloride and water when we form that above. So what's our product here going to be? What do we think? So we're going to form water and 1 salt. What do you think our salt's going to be? Calcium sulfate. Excellent. Okay, so we need to know the charge on a sulfate ion. Does anyone remember the charge on the sulfate ion? If not, have a look at sulfuric acid. We know that there's 2 hydrogens reacting with 1 sulfate ion. So what does that tell us about the charge of the sulfate ion? Excellent, people are saying 2-. So if the sulfate ion has a 2- charge and the calcium ion has a 2+ charge, what do you think the chemical compound formula is for calcium sulfate? So 2+ for calcium, 2- for sulfate. What do you think that means? What will be the formula for calcium sulfate? Excellent, because it's 2+ and 2-, it's just going to be CaSO4. And that's because calcium has 2 electrons that it wants to give and sulfate wants to accept 2 electrons. So we only need 1 calcium reacting with 1 sulfate. And then remember, the other product will be water. Okay, so now we just need to balance it. If we have a look, we've got 1 calcium, 1 calcium, 2 hydrogens, 2 hydrogens, but there's also 2 hydrogens in our hydroxide. So at the moment, there are 4 hydrogens on the side of the reactants. So we probably need to put a 2 here. Our sulfates are 1 and our oxygens are 2. So we've made that all equal. So the only change we had to make was to double that water there. Just to go over that again, 1 calcium, 1 calcium, 1 sulfate, 1 sulfate, 4 hydrogens, 2 plus 2 is 4 hydrogens, and then 2 oxygens and 2 oxygens. Remember, the oxygens and sulfate we've already accounted for because we took sulfate as a whole ion, just like in the reactant and product side. Now we have a balanced equation. We said that the number of moles of calcium hydroxide was 0.005. So what are the number of moles of sulfuric acid then, using the balanced equation? So we've got 0.005 moles of calcium hydroxide. What are the number of moles of sulfuric acid? So everyone that gave me the formula for calcium sulfate, well done, you were all correct. We've got 0.005 moles of calcium hydroxide. Does anyone know the number of moles of sulfuric acid then, using the equation? What do we think? Okay, so if we use the equation, we know that there is a 1-to-1 ratio. Excellent, so people are saying 0.005. So there's 1 calcium hydroxide reacting with 1 sulfuric acid. So that means 0.005 moles of calcium hydroxide reacts with 0.005 moles of sulfuric acid. So then the next step is we want to calculate the concentration of sulfuric acid, as it said in the question. We will note that it says grams per decimeter cubed. At the moment, let's just do it in moles per decimeter cubed, and then we'll convert to grams per decimeter cubed in just a second. So we've got a volume of sulfuric acid as 10. So remember that concentration equals moles over the volume. We've got the number of moles, so we divide by the volume. The volume is in centimeters cubed, so we need to divide by 1,000 to get it in decimeters cubed. And it's going to be at 0.01. So 0.01, so 0.005 divided by 0.01. What do we think then? What's the concentration in moles per decimeter cubed? You should have got an answer of 0.5 moles per decimeter cubed. Okay, so the final step then is to convert it to grams per decimeter cubed. Does anyone remember how we convert to grams per decimeter cubed? There's one final step. So we've got it in moles per decimeter cubed. We want to convert to grams. Does anyone remember that final step? Excellent, multiply by the MR. Really well done everyone for remembering what we went over on Monday. So we've got our moles of sulfuric acid, so we need the MR. I'll tell you that the AR of hydrogen is 1, the AR of sulfur is 32, and the AR of oxygen is 16. So what's the MR of hydrogen sulfate? Someone's asking me what is AR. AR is the relative atomic mass. So if we look on our periodic table over here, the atomic mass is the top number. It's the atomic mass of that, and we use that to represent the number of grams because the atoms are so small, so we use that as a relative form of the number of the weight or the mass of that each element. Okay, yep, so what's the MR of sulfuric acid? Does anyone have any answers for that? So remember, we do 2 hydrogens plus 32 plus 16 times 4. Okay, so we've got some answers coming in. So it should be 32 plus 16 times 4 plus 2, which gives you an answer of 98. So well done to people giving me 98. And then as we do 0.5 times 98, which will give you an answer in grams per decimeter cubed. 0.5 is just a half, so it will be 49. So your answer in grams per decimeter cubed will be 49 grams per decimeter cubed, and that's the sulfuric acid. Okay, so before we move on to gas volumes, does anyone have any questions then on concentrations or titration reactions? Okay, so let's move on to gas volumes. So gas volumes, as I said, is a higher topic. Someone's just asking, would they give you the AR values? They do tend to give you the AR values in all questions. If they don't, just look at your periodic table. As I said, it's the top number. It's the atomic mass. Okay, so volumes of gases, it's a higher tier topic, and there are a couple of things you need to know to be able to implement this formula. So the volumes of gases can be produced from the balanced equations, which is exactly like concentrations and all the equations we've looked at over the past couple of weeks. All of the equations pretty much rely on balanced equations. 1 mole of any gas is 24 decimeters cubed. And what that means is that a lot of scientists looked at, well, what is the volume of 1 mole? And they found that 1 mole of any gas, it doesn't matter which gas it is, it's 24 decimeters cubed. And the key thing is that is at certain conditions. So it must be at room temperature, which they've defined as 20 degrees, and at normal pressure, which is 1 atmosphere. So this only applies when we've got things at room temperature and at normal pressure. So the value of 24 decimeters cubed is known as the molar gas volume. And the main equation that we need to be able to use is that the number of moles of any gas is the volume of that gas divided by that molar gas volume. Okay, so I've got some questions then. So remember, the number of moles of any gas equals the volume of that gas divided by 24. And this is only for gases, nothing else. So we're going to slowly build up then the question difficulty. So we start off first with a question that says, what volume of gas would be occupied by 28 grams of helium? So the first thing we notice there is we've got grams of helium and our question has moles and volume in it. So does anyone know how we can convert this 28 grams to either a volume or to the number of moles? What do we do to a mass to either convert it to a volume or the number of moles? Which one do we think we can convert it to? Moles. Excellent. So what's the equation then to convert a mass into moles? Good. Moles equals mass over mR. So if moles equals mass over mR, we want the mass. So what does that mean that the mass is equal to? If we rearrange that equation, what's the mass equal to? Or the moles equal to? The mass is 28 grams, and so what's the MR? Does anyone know the MR of helium? If not, we can look at our periodic table. So our periodic table, helium's over here. So what's the mass, the MR or AR of helium? It's not 2, it's 4. Remember, it's the top number. So the 2 represents the number of protons. The relative atomic mass is the top number. Excellent. So what we would do is 28 divided by the MR, and the MR is 4, so 28 divided by 4 is 7. So that means the number of moles is 7. So the volume of gas will be 7 equals the volume, X divided by 24. If we rearrange that equation in our triangle form, we've got moles, volume, and 24. So the volume is the number of moles times 24. So if the number of moles is 7, it's 7 times 24. So what's 7 times 24? Okay, someone saying 168, exactly, well done. So that means the answer to this question is that the volume of gas occupied by 28 grams of helium is 168. And remember, that's in decimeters cubed. Well done. Okay, so the next question. What volume of gas would be occupied by 15.3 grams of nitrogen dioxide? So again, we need to convert this grams into moles. We've got our equation on the right here that moles equals mass over mR. So our mass is 15.3. We need the mR of nitrogen dioxide. They've told us that that's NO2. If we look at our periodic table, we know oxygen is 16. That's the AR of oxygen, and nitrogen is 14. So it's going to be 14 plus 32. That's 16 times 2. So 14 plus 32, which is equal to 46. So 46, so it would be 15.3 divided by 46. So what's the number of moles of nitrogen dioxide? What do we think? What's the number of moles? Remember, I said the number of moles is the mass divided by the MR. We've said that the MR is 46 and the mass is 15.3. So what's the number of moles? So you should get an answer of 0.3326. We don't need to round it up yet because we're not at that final part. So just keep the answer that you've got on your calculator. It's really important you keep that answer. So then we want to convert it into the volume of gas. So we use this equation over here. So the number of moles equals volume times 24, divided by 24. And we know that the volume is the moles times 24. So if we times our answer by 24, we'll get a volume in decimeters cubed, which comes out to be 7.98 to 3 decimal places. Or sorry, 3 significant figures. And that is in decimeters cubed. Okay, we won't do the second and the third and fourth question there. We'll move on to some slightly trickier ones, slowly building that up. Does anyone have any questions about those questions so far, though? So just the answer was 7.98 decimeters cubed. So we're implementing the moles equals mass over MR, and then the gas equation, which is moles equals volume over 24. Excellent. Okay. So now there's 2 types of questions that you could get with gases. They're obviously going to come from equations, like I said in one of the first slides. But if we've got an equation that is all gases, it's really easy to work out. We can just use the balanced equation to help us. You don't need to do any calculations. So what I mean by that is this question here is methane gas, which is CH4, burns completely in air. So that means it burns with oxygen. And it forms carbon dioxide and water. So CO2 plus H2O. Let's just balance that equation. So we've got 1 carbon, 4 hydrogens, but only 2 hydrogens. So let's make that a 2. We've now got 4 hydrogens. We've got 4 oxygens, but only 2 here. So we need to make that a 2. So now we have 1 carbon, 4 hydrogens, 4 oxygens, 2 here plus 2 here, which makes 4. So that's our balanced equation for methane burning with oxygen. And what we can see there is it's all gases. So this is saying what volume of oxygen gas is needed to burn 280 decimeters cubed of methane. Now, the nice thing about these questions is that when we've got a volume of, say, 280, we don't need to do any calculations. We can just look at the balanced equation. And we know that 1 mole of methane reacts with 2 moles of oxygen. So this is asking for the volume of oxygen gas. All we need to do is multiply this number by 2, which is 560. So when you've got all gases in an equation, you don't need to do anything. You can just look at the ratios of the gases to work out the volume. But the key thing is that only applies when we've only got gases in the equations. If you've got anything but gases in there, you can't do that. You need to use the equations that we've already covered. So it's really important that we look at, if there's all gases, we can just pretty much use multiples of what's in the equation. If we do a second example of that, we've got hydrogen reacting with chlorine. Again, we know chlorine is a gas. So hydrogen reacting with chlorine, they go around in pairs. Hydrogen chloride forms. Okay, so now what we can see to balance that, there's 2 hydrogens and 2 chlorines on the reactant side. So we need to put a 2 on the product side, and they are all gases. So again, if 35 centimeters cubed of chlorine reacts, what volume of hydrogen chloride is formed? So 35, so what do we think? If we look at our balanced equation, what volume of hydrogen chloride is formed? 35 is our volume of chlorine. These are all gases. What volume of hydrogen chloride is formed? What do we think? 70, excellent, well done. So that's because there's 1 mole of chlorine reacting with 2 moles of hydrogen chloride. So again, that would just be 70. Well done. Okay, so that's one type of question. The second type of question is when we don't have just gases in the equation. And that is when we have, as well as gases, we've got solids in there, we might have some liquids in there, in which case we need to use the gas equations. For the person that's asking me, are you saying if they're all gases, you don't have to worry about moles? Yes, exactly. So if they're all gases, you only need to look at the big numbers or the balanced equation, so the big numbers in front of the balanced equation, so that we can see, well, what's the ratio of one gas to another? And it's all because 1 mole of gas has a volume of 24. So when they're all gases, the volumes will stay the same based on how many moles of each there is. Remember, I'm here talking about the ratio in moles, so you don't need to calculate the number of moles. What I mean by that is, if we look at our equation, effectively 1 mole of methane reacts with 2 moles of oxygen, or 1 methane reacts with 2 oxygens. Someone's asking me, how did I get the answer of 70? That's because 1 chlorine forms 2 hydrogen chlorides. So 1 chlorine has a volume of 35, so therefore the hydrogen chloride will be double 35, which is 70. Remember, this only applies when we're looking at gases. Okay, and don't apologize for asking me questions, that's absolutely fine. Okay, so then the final type of question we need to be able to answer, as I said, is when we don't have just gases in the equation. So we'll look at the first one here then. Calcium carbonate decomposes to form calcium oxide and carbon dioxide. So let's first of all write that balanced equation out. So we've got calcium carbonate, CaCO3, it decomposes to form calcium oxide plus carbon dioxide. Let's see if that's balanced. We've got 1 calcium, 1 carbon, 1 carbon, 2 plus 1, 3 oxygens, 3 oxygens. So that's a fully balanced equation. Calculate the volume of carbon dioxide produced using 300 grams of calcium oxide. 300 grams of calcium carbonate. Assume that the gas is at room temperature and pressure. So effectively, the only gas here is carbon dioxide. The others are not gases. So what we need to do first of all then is we need to know the moles of carbon dioxide, because remember our equation is that the moles equals the volume divided by 24. And if we want to know the volume of carbon dioxide, we need the moles. To calculate the moles, we need to know the moles of calcium carbonate, and that's because they've told us that there's 300 grams of calcium carbonate. So again, it's just about using that equation, moles equals mass over mR. So if we know our mass is 300 grams, we can calculate the moles of calcium carbonate. So the mR of calcium carbonate, the AR of calcium is 40, the AR of carbon is 12, and the AR of oxygen is 16. So what's the MR of calcium carbonate? So I've given you the ARs of all three of them. What's the MR? So it'd be calcium plus carbon plus 3 oxygens. So 52 plus 48, which gives us a nice number. What's 52 plus 48? And therefore, what's the MR? 100. Brilliant. Okay, so we've got our our MR of calcium carbonate, and that's 100. So if our mass is 300 and our MR is 100, how many moles of calcium carbonate are there? So it's 300 divided by 100. How many moles are there of calcium carbonate? 3. Excellent. Well done. So there are 3 moles of calcium carbonate. So how many moles of carbon dioxide do we form? If we look at that balanced equation, what's the ratio of calcium carbonate to carbon dioxide? So the ratio is 1 to 1. Excellent. So if there are 3 moles of calcium carbonate, how many moles of carbon dioxide are going to be formed? 3. Brilliant. Well done, everyone. So if there are 3 moles of carbon dioxide, we can now just use our equation that the moles equals volume divided by 24. We want the volume, so we rearrange. So the volume equals 3 times 24. So what's 3 times 24? And you'll get a volume. Excellent. So someone said 72. Brilliant. Yep, everyone's coming in with 72 now. So that's the exact right answer. So it's 72 decimeters cubed. And it's really important you say decimeters. Okay, excellent. We'll do one more of those questions, and then we'll do a few exam questions on all of the topics we've covered. So calcium, let's do this one here. Calcium reacts with chlorine to form calcium chloride. So calcium, let me change my pen color. Okay, calcium reacts with chlorine to form calcium chloride. So Ca is a 2+ ion. Chlorine is in group 7, it's a 1- ion. So when they react, we have CaCl2, and that's because this is 2+, this is 1-. So when they want to react, we need 2 chlorines to react with calcium so that calcium can lose its 2 electrons and chlorine can therefore gain 2 electrons. So calcium chloride, that's all it is. So it's calcium plus chlorine goes to calcium chloride, and we can see that that is also fully balanced. Calculate the volume of chlorine, so we know this is our gas, required to react with 80 grams of calcium. So exactly like we did before, we need to calculate the moles of calcium. So the moles of calcium will be the mass divided by the AR of calcium. Calcium has an AR of 40, so it's 80 divided by 40. And remember, you can get the AR from looking at the periodic table. So the AR of calcium is 40, so 80 divided by 40 is 2. Excellent, well done everyone. So the number of moles of calcium is 2. So how many moles of chlorine are there? If there are 2 moles of calcium, how many moles of chlorine? Excellent, 2. And that's because there's a 1-to-1 ratio. So there's 1 calcium and 1 chlorine. So that means there's a 1-to-1 ratio, so 2 moles of chlorine. And then to calculate the volume, again, we do 2 times 24, because remember our gas equation says that the moles equals volume divided by 24. So what's 2 times 24? 48. Excellent, well done everyone. So the volume of chlorine formed is 48 decimeters cubed. Excellent. Okay, so before we move on to a summary of all the topics we've covered, does anyone have any questions? I've just had one come through that says, how do you get 2 moles of chlorine? That's because if we've got 2 moles of calcium, remember we did that by doing the mass divided by the MR. In this case, it was the AR. We got told there was 80 grams of calcium, so the mass is 80. The AR of calcium is 40, so that means 80 divided by 40 is 2. So there are 2 moles of calcium. If we look at our balanced equation, 1 calcium reacts with 1 chlorine. So if there are 2 moles of calcium, there are also 2 moles of chlorine. So that means then that we use our gas equation, which says that the moles equals volume divided by 24. If we rearrange that, the volume equals moles times 24, which gives us 48. Is moles short for molecules? No, moles is the full version. If you go back to last week, we had a look at moles, I think on Monday last week, and we talked about Avogadro's number and what the moles represents. Okay then, so this is a summary table of everything that we have done over the past 2 weeks on quantitative chemistry. So just as a quick recap, we started off with the relative atomic mass, which we said is when we've got different isotopes and we calculate the mean AR of all the isotopes. So in this case, we know that, for example, chlorine has an AR of 35.5. And the reason for that is that it has two isotopes, one that has a mass of 35 and one that has a mass of 36. And they are both in abundance of 50%, which means that in the Earth, there's 50% of 35 and there's 50% of 36. So that means that the overall or average AR is 35.5. So that's how we calculated the AR. Yeah, I'll write off what got cut off in just a second. It's the equation that got cut off is the equation we looked at today. It's the moles of gas. So relative formula mass, again, we've been doing this lots. So sum of every AR in the compound or molecule. So for example, hydrogen chloride, the MR of that would be hydrogen's AR, which is 1, and chlorine's AR, which is 35.5. So the MR would be 36.5. Moles and masses, again, we've used that today, where the moles equals mass over MR. And this is just saying that we use it in empirical formulae, balanced equations from masses, finding limiting reactants, and masses from equations. The percentage yield is equal to the actual mass of the product divided by the total theoretical mass. So often in reactions, we'll produce, say, a mass of something that is 1.2 grams, but when we calculate it, you might actually be able to produce 2 grams of it. But in practice, you won't ever form 2 grams, and that's just because the reaction might be reversible, there might be some, it might not react, all of the reactants, and therefore you don't tend to produce everything that you would calculate that you should produce. So the percentage yield is about how much did you produce over how much is theoretically possible. So here it will be 1.2 divided by 2 times 100. The atom economy is similar to percentage yield, but it's about, of all the elements in the reactants, what goes into the product that you want. So for example, if we want a product of iron, and we know that iron, for example, decomposes, so FeO2, so it's F3O2, decomposes, hold on, it's F2O3, let me rewrite that, Fe2O3. Okay, if that decomposes to produce iron and oxygen, for example, we would look at, well, what is the AR of all of the reactant and what forms in the product, and then we do what's the product over the reactant. Again, I'm going over these quickly. If you want to know more detail, please go back to last week's sessions where we covered all of these questions in a lot of detail. Concentration, we did last Friday. The percentage yield represents how much mass you produce over the total theoretical mass. So as I said, you don't always produce what you would calculate. And that's because of, as I said, not all of the reactant reacting and the reaction being reversible. So there's lots of different reasons. You don't tend to produce what you should. And that's just because of different limitations of reactions. So concentration, we've looked at that today right at the beginning. So mass over the volume. And then molarity, which again is a concentration reaction, which is moles over volume. And we tend to use that in titration calculations. And the final one that got cut off is the moles of gas. So remember, the moles of gas then is the volume divided by decimeters, divided by 24. And we use those in gas volume questions. Okay, so if there's no questions on any of those, and as I said, it's a very quick run through, and that's because we've gone over it in a lot of detail in previous questions. Someone is asking me to go over molarity. So molarity is concentration in moles per decimeter cubed. Right at the beginning of today, we used that equation to do a titration calculation. So it's exactly the same as concentration, but instead of it being in grams, we do it in moles. Okay, so let's do some exam questions. So the first question here, the equation for the reaction is magnesium plus water produces magnesium oxide plus hydrogen. The teacher uses 1 gram of magnesium. Use the equation to calculate the maximum mass of magnesium oxide produced. So which equation are we going to be using here? So the teacher used 1 gram of magnesium. Use the equation to calculate the maximum mass of magnesium oxide that can be produced. Any ideas? How are we going to tackle that question? Yeah, mass over AR. So remember that is our main equation. So moles equals the mass over the AR or MR. So here we've got 1 gram of magnesium and we want to know how much magnesium oxide is formed. So again, we look at how many moles of magnesium are there. If I go on to the next page, someone always asks me, it says it here what the AR is. They will give you the AR. So it's magnesium reacts with oxygen. Oh, sorry, I think it was with, let me go back. So magnesium, sorry, reacts with water to produce magnesium oxide plus. So magnesium plus water will produce magnesium oxide plus hydrogen gas. So that was the equation. So let's think then, we've got 1 gram of magnesium. How many grams of magnesium oxide are going to be produced? Do we need to balance the equation? It's a very good question. If you have a look, it is already balanced. They will usually tell you to balance it if it's not balanced. So there's 1 magnesium, 2 hydrogens, 2 hydrogens, 1 oxygen, 1 oxygen. So it's all balanced. So we need to find the number of moles of magnesium, which is equal to the mass of magnesium, which was 1 divided by the AR, which is 24. So the number of moles of magnesium is 1 divided by 24. So if you do that on your calculator, you should get an answer of about 0.0416 recurring. Then if we look at our balanced equation, the ratio of magnesium to magnesium oxide is 1 to 1. So if there are that many moles of magnesium, there are also that many moles of magnesium oxide. So to calculate the mass then, we know that moles equals mass over MR. So the mass is equal to the moles times the MR. So the MR of magnesium oxide will be 24 plus 16, which is 40. So yeah, excellent. So we do 40 times 0.04166, which gives us an answer of 1.6 recurring. Remember, we always do it to 3 significant figures. So this will give you an answer of 1.67 grams. Good, excellent to everyone that gave me answers for that. Very well done. Okay, so again, incorporating another thing, so percentage yields then. The teacher's demonstration produced 1.5 grams of magnesium oxide. Use your answer to calculate the percentage yield. So we got 1.67 as the maximum mass. The teacher produced 1.5. So what's the percentage yield? Does anyone know? How do we calculate the percentage yield of that then? So we've got a maximum mass of 1.67. The teacher produced 1.5. Yep, good. So it's actual mass divided by theoretical mass. So someone said it's 1.67 divided by 1.5. Not quite, it's the other way around. So remember, she produced 1.5. The theoretical mass is the mass that we said could be produced, which is 1.67. And then, yep, someone said 1.5 divided by 1.67 times 100. Great, so what's the answer then? 1.5 is the mass that she produced, the actual mass. The theoretical total mass is 1.67. So we do 1.5 divided by 1.67 times 100. And yes, to 3 significant figures, you should get an answer of 89.8%. Excellent, well done. So again, that's a classic exam question where they incorporate 2 types of equations. So give 1 reason why the percentage yield is less than 100%. So I gave you 2 reasons on the previous slide as to why we wouldn't have a percentage yield of 100%. Does anyone remember either of those 2 reasons? There's lots of reasons, but does anyone remember either of those 2 reasons? So why would we not have a percentage? Good, not all the reactants will react. So specifically here, maybe not all the magnesium reacted. Yep, there could be external factors affecting, there could be waste products, there could be spillages, excellent. It could be a reversible reaction, good. So the answer I like to give on this question is that not all the reactant may react. So specifically, not all the magnesium may react. Well done, okay. Let's go on to another question. Calculate the relative formula mass of copper oxide. So what's the relative formula mass of copper oxide? So these are all mixed questions, both foundation and higher tier. The aim is to just hopefully expose you to lots of different types of questions. Yep, it's 80. Good. So it's Cu plus O. So Cu plus O. So 64 plus 16, which is 80. What's the percentage of copper in copper oxide? So this is kind of like atom economy, but not quite. So what's the percentage of copper in copper oxide? What do we think? Someone's asking me to go over the first exam question. I'll go over it at the end if there's time. Okay, so remember, to get the percentage of something in something else, we do 64 divided by 80 times 100 as a percentage. So what's 64 divided by 80 times 100? Excellent. Good. So people are saying 80%. Excellent. Well done. That is correct. Okay, I'll take a brief pause here for any Q&A questions. If not, we'll do some more exam questions. It doesn't look like there are any Q&A questions. If anyone does have any, just pop them into the Q&A or chat function, and I will answer them now. No? Okay, that's fine. Oh, someone's just asked me, what's the difference between atom economy and percentage yield? Okay, that's fine. So let's go back to the previous question. On this question, we calculated the percentage yield of magnesium oxide formed. And we said that the percentage yield was 1.5 divided by 1.67. So that is the mass produced by the teacher. So that is the actual mass that you produced in an experiment, which was 1.5, divided by the maximum mass that can be produced. So if someone does this reaction and puts it under all of the right conditions that it needs to be under, makes sure all that magnesium reacts and there's no kind of reversible reaction, in theory, they should be able to produce 1.67 grams of magnesium oxide. So the percentage yield says, okay, but what's the percentage of how much we produced over the total? So we did 1.5 divided by 1.67, and then we times by 100, because again, it's a percentage yield. The atom economy would be, well, what's the AR of the reactants? So magnesium, for example, has an AR of 24. In water, the MR here, because it's the formula, would be hydrogens, 2 hydrogens, which would be 2 because the AR of hydrogen is 1, so there's 2 of them, plus oxygen, which is 16. So the total would be 18. So the total AR of the reactants is 24 plus 18, which is 42. And then the magnesium oxide, we look at the MR of that, and we already worked that out, which was just 24 plus 16, which was 40. So the atom economy is, well, what's the MR of the product we wanted, 40, divided by the MR of all of the reactants, which was 24 plus 18, which was 42. So the atom economy would be 40 divided by 42 times 100. Okay, so that's the atom economy. Someone's asking me, is this the last session for these topics? Yes, tomorrow we will be going on to reaction energies. Would higher have to learn all the equations, or will we be given them? So the only higher equations are the titration calculations and the gas volume calculations. How can you explain the term concentration of a solution? So the concentration of a solution is how many, for example, if you think about hydrogen chloride as hydrochloric acid, hydrogen chloride is dissolved in water. So the concentration of hydrochloric acid, well, is how much hydrogen chloride is dissolved in that water. Obviously, if we dissolve more hydrogen chloride in that water, it becomes more concentrated. Whereas if there's less hydrogen chloride in that water, it becomes less concentrated. So that's what concentration of a solution means. What exam boards are these for? All of these equations are in all of the exam boards. I've checked that. So Edexcel, AQA, and OCR have all of these questions. They all tend to be fairly similar. So you need to know all the equations. Okay, let's do another exam question then. So it's up to you guys. Do you want to do this type of question, or do you want to do a concentration question? What do you feel like you want to have more help with? Because we've not got too much time left, so I want to do what you think would be most helpful. So either we can do concentration, or we can do some more kind of masses and moles. Concentration, yeah, okay, they tend to be the harder questions. Okay. Right, let's start here. All right, so a student used a pipette to add 25 centimeters cubed of sodium hydroxide of unknown concentration to a conical flask. The student carried out a titration to find out the volume of 0.1 moles per decimeter cubed of sulfuric acid needed to neutralize that sodium hydroxide. Describe how the student would complete that titration. Okay, so this is going back to the method of titration. I don't want to spend too much time on this, so just as a brief run through, we've been told that the sodium hydroxide is in the conical flask. That means our alkali is in that conical flask. So the next thing we need to do is add an indicator. The one I tend to use is phenolphthalein, and we know that is pink in alkali. So when we add it, the solution in the conical flask will be pink. We then need to add our sulfuric acid to a burette, and remember, we then add the sulfuric acid to the conical flask dropwise, and we keep swirling that conical flask. And as that sulfuric acid gets added to the conical flask, it will turn colourless, but only for a second. When you swirl it, it will all dissolve and it will remain pink until you reach the neutralization mark. When you reach the neutralization mark, that phenolphthalein will go from pink to colourless. So here the mark was for talking about the burette in which the sulfuric acid would be, your indicator and the colour change. So it depends on which indicator you use. So it's really important that whichever indicator you use, you talk about the colour change of that indicator and then about adding it dropwise. All right, so that's the answer for that question. Okay, so the student carried out 5 titrations. Her results are shown in the table below. Concordant results are within 0.1 centimeters cubed of each other. Use the student's concordant results to work out the mean volume. So hopefully you remember what concordant means from Monday. So here they've told us though that it's when results are within 0.1 of each other. So which results in this table are within 0.1 centimeters cubed of each other? Does anyone know which results are within 0.1 of each other? I'll tell you there are. Okay, someone's saying 3 and 5, almost, you're missing 1. Someone's saying 3, 4, okay, and finally, so it's 3, 4, and 5. These two are definitely concordant, they're exactly the same, and this one is also concordant. It's within 0.1 centimeters cubed, so those 3 are all concordant. Well done. So then how do we work out the mean volume? Does anyone remember? If we've got 3 concordant results, what do we do to calculate the mean volume? It's just like in maths, to calculate the mean of some numbers. How do we do that? So we've got 3 volumes, and we want the mean volume. What do we do? Add up the 3 and divide by 3. Excellent. So we add them all up. So if you do 27.15 plus 27.15 plus 27.05, we then divide by 3 because there are 3 answers. You should get an answer. So does anyone have an answer for that then? Yep, 27.1 to 3 significant figures. So 27.1. And that's about what we would expect. We expect it to be closer to 27.15 than 27.05 because there are 2 that are 27.15. Okay, so that's our volume of our sulfuric acid. Remember then that the concentration is 0.1. The equation for the reaction is below. Calculate the concentration of the sodium hydroxide. So they've given us a nice balanced equation, which was nice of them, and we want to calculate the concentration of sodium hydroxide. We've got a volume and a concentration of sulfuric acid. So what's our first step? We've got a volume and concentration of sulfuric acid. What's our first step? That's the one that we've got the most information about. What do we think? So we've got a volume and a concentration of sulfuric acid. So what's the first step then, so that we can calculate the concentration of sodium hydroxide? Okay, so the first step is to calculate the number of moles. So remember concentration equals moles over volume. So here we've got the volume, which we've been told is 27.1, or we calculate it to be 27.1. Remember, it's in centimeters cubed and we need it in decimeters cubed. The concentration is 0.1. So the number of moles will be 0.1 times 0.0271. And the reason for that is because we need to convert centimeters cubed to decimeters cubed, which we do by dividing by 1,000. So 0.0271 times 0.1, that's just going to move the decimal place one place. So you get an answer of 0.00271. That's the number of moles of sulfuric acid. If we look at our balanced equation, if that's the number of moles of sulfuric acid, how many moles of sodium hydroxide are there then? There's 0.00271 moles of sulfuric acid. How many moles of sodium hydroxide will there be? Look at the balanced equation and see what the balanced equation. Double it. Excellent. And that's because there's 2 sodium hydroxides reacting with 1 sulfuric acid. So if there are 0.00271 moles of sulfuric acid, there will be double that number of moles of sodium hydroxide. So that gives us 0.00542. And then we need to know the volume of sodium hydroxide. So hopefully you remember it was right at the beginning of the question. They told us here that 25 centimeters cubed of sodium hydroxide was in that conical flask. So if there are 25 centimeters cubed of sodium hydroxide, we want the concentration. The concentration is moles over volume. So remember, it's in centimeters cubed, so we need to convert it into decimeters cubed. So the concentration will be 0.00542 divided by 0.025. So 0.00542 divided by 0.025, which should give you an answer of 0.217 to 3 significant figures, moles per decimeter cubed. Okay, excellent. Good, well done everyone that gave me answers to that. Excellent. So we went over a few exam questions today. We probably haven't got time to go over any more exam questions. So if anyone has any questions on quantitative chemistry, feel free to send them in. As I said, we have covered all of the equations before in previous webinars, so please do rewatch them if you're unsure about any of these equations. We've definitely gone over loads of questions, and all the questions that we've done in the sessions are exam questions. They're never questions written by me, like for example, they are all exam questions. So we've done lots of exam questions already on all of the topics. Okay, if there are no questions then, I will see you tomorrow where we'll be starting our next topic, which will be looking at reaction profiles and energies in reactions, so exothermic and endothermic reactions.
Brilliant, thanks so much, Aman. That was a really, really useful lesson. Great topic summary. Yeah, and as Aman says, join us for the next chemistry session tomorrow, which I believe is at 3:15. And if you join us for any other sessions, we have maths coming up next. That's a foundation maths session, then physics, then one of our regular math sessions after that. And as Aman says, you can catch all the previous videos on YouTube. Brilliant, lovely to see some nice feedback in the chat. Thanks very much guys for attending today, and see you in another session soon. Bye.
Bye.